Next, moving to the next problem on step bar. That is, consider bar shown in figure. Determine the displacement at node 2 and reactions at support, stress, strain. Take E1 is 70 GPa, E2 is 200 GPa for element 1 and 2 respectively. That means this is also a kind of same previous problem. It is also made up of two different materials, and in the problem they given in the figure, it is having a diameter D1. 5 is a diameter. This is circular in nature, therefore 0.01 meter, and 5 to D2 is 0.02 meter. This is a 0.2, this is a 0.3 meter length. And here you can observe that there are two different load. Here it is 300 kiloton axial load, and here this called distributed load, that is 800 kiloton per meter. That means this bar is subject to both axial or concentrated load as well as distributed load. So we need to find same stress, strain as well as reactions and nodal displacement. Therefore again we can write that first we need to write the data corresponding. If you divide it, this is section 1 and section 2, therefore corresponding it called as L1, L2, A1, E1, L2, A2, E2, like that. A1 we need to find first. According to the diameter is given, pi d1 square by 4, A2 is pi d2 square by 4. Let's keep it in everything meter only, that's the better. And this is 800 kilonewton per meter, convert into Newton, and this also into Newton. Now step number 1, we need to divide the discretization forces. For that we need to write a element model. So this is an element model made up of two material with the 3 nodes. Here the nodal displacements are Q1, Q2, Q3, and nodal forces are F1, F2, F3, and here axial load, and here distributed load, element 2. At node 2 axial load also there. Now next step is we need to find the individual stiffness matrix. For the element 1, K1 is equal to A1, E1, L1, 1 minus 1 minus 1. Substitute all the values, therefore keep only 10 power value, and remaining you transfer, multiply by inside. Therefore we got a K1 is this much, K1 is this much. Now K2, similarly for element 2, K2 is A2, E2, 1 minus 1 minus 1 1. Substitute corresponding A2, E2, L2 values, and K2 become 10 power 6, 209.33 minus 209.33 minus 2.9, 209.33 and 209.33 plus. So corresponding at the top and right side you will write the node value 2, 3, 2, 3 for K1, 1, 2, 1, 2, row and column numbers. And finally step number 3, we need to assemble the global stiffness matrix, that is K1 plus K2. Similarly we need to add both the things as I explained in the previous problem. You add it, you can get this much matrix. The matrix is become this much, 3 by 3 matrix, 3 cross 3 matrix. And now step number 4, we need to find the global force vector and displacement vector. So here keep this in mind, when you are writing the axial force vector at node 2, both axial force and distributed load acting, therefore calculate the nodal force separately. That means that you can see now I am taken separately the nodal forces. For element 1 we are considering axial force, that is F1, F2. In F1 is 0, F1 is here 0, and F2 we can take in as axial load, that is minus 300,000. Similarly force due to distributed load, that is distributed FD, D stands for distributed, here F axial, therefore that is F2, F3. Again F2 is a distributed load. So as I told, it is uniformly acting. Therefore in the previous problem we seen that when distributed load is given, we need to convert into a point load, that is P0 into L by 2. Both node and 2 and 3 it is uniformly acting, therefore take common, that is average of that. P0 L2 corresponding node 2 element 2, it is length is L2 by 2. Therefore substitute both the values, that is become 120 into 10 raised to 3, and multiply by inside, that is 120 into 10 raised to 3, 120 into 10 raised to 3. This is very important. So we taken in this problem axial load for the element 1 and element 2 subjected to a distributed load. Now for the global force vector we need to add these two. So therefore if you add it, if you add this one in the same way, how you are adding the matrix for the global stiffness matrix, in the same way assembly you do it. So this is for this is 1 2, this is 2 3, and this is become 1, this is 1 2, this is 2 3, and this is become 1 2 3. 1 plus 1 is 0. Next 2, here minus 300 plus 120. Next 3, here only 120 into 10 raised to 3, and 3 minus 300 into 10 raised to 3 plus 120 into 10 raised to 3 become minus 180 into 10 raised to 3. Therefore this is global force vector becomes 0, minus 180 into 10 raised to 3, and 120 into 10 raised to 3. Similarly, global force vector Q is equal to Q1, Q2, Q3. Now finally substitute the equilibrium equation KQ is equal to F, substitute corresponding values and apply the boundary condition. Here also node 1 is fixed, node 3 are fixed, therefore Q1, Q3 are both are 0. Apply the elimination technique, therefore corresponding first row, first column, third row, third column. We need to eliminate first row, first column, third row, third column, and remaining thing left is this much. Now solve Q2, therefore we got minus 0.76 into 10 raised to minus 3 meter. Now finally we need to determine the stress. For that we require strain B1 into Q, B2 into Q. Substitute the strain displacement matrix 1 by L1, 1 minus 1, Q1, Q2. Therefore epsilon 1 become minus 3.8 into 10 raised to 3, and epsilon 2 become 2.53 into 10 raised to minus 3. Finally sigma 1 become epsilon 1 to E1, that is minus 2.66 into Newton per what is that E1 we substituted in a meter, no? So it is not mm square, it is a meter square. Newton per minus 2, so this is Newton per meter square. Negative indicate compression. Section 1 it is under compression, and sigma 2 is 506.6 Newton per meter square. It is positive, therefore it is under tension. And finally find the reaction, that is R is equal to KQ minus F. Substitute K value, Q value and F value. We know Q1, Q3 as 0, and Q2 we got as minus 0.76 into 10 raised to 3. F1 F1 is 0, and F2 anyway in a global stiffness matrix we got this one, right? Where is that? Wait, here global in a previously we find out what is global force vector, that is 0, minus 183 into 10 raised to 3, and 120 into 10 raised to 3. Same we substituted here, and finally we are finding the reactions. So R1 we get as 20.88 kilonewton. I found out that similarly the R3 become 39 kilonewton. Let's see, let's validate this value. See the problem now. Take a break. So what is the total force applied? You observe, see the total force applied is, let's take 300 is under like a compression, therefore minus 300 minus 300, and 800 distributed plus 800 for a length of how much into 0.3. So therefore for a length of 0.3, therefore this is become 6 how much 60. If you do it, this become 60 kilonewton. So 300 minus 300 plus 800 for a length of 0.3, therefore that is become 800 into 0.3, therefore become totally 60 kilonewton. So let me cross verify the reaction value now. Let me cross verify the reactions value. Yeah. So how much we got? R1 is R1 plus R2. R1 plus R2. R1 we got 20.88 plus R, not R2, sorry, R3 is 39. So it is almost 59.88. So approximately equal to 60 kilonewton. So then answer is right. So like this you can validate. If the applied force equal to reaction force, then your problem is correct. So this complete the problems on steppered bar. So we'll move into the next case is a taper bar.